Welcome, everyone. My name is Jason Resch, and today I'm going to be sharing with you my fascination for what I call magical math. This is math that does things that's so astonishing and borders on the impossible. But it is possible, and in fact, your computer is doing some of that math right now in order to support this presentation. Today, we're only going to kind of dip our toes in. We'll see a little bit about how it works. But if you're interested, at the end of the presentation, I have all the links to all the background if you want to have a deeper dive. And I'm also happy to answer any questions you may have later by email and so forth. If you have any questions, we should have time for questions at the end of this talk. Just take a note of the slide number and we can return to it at the end. So with that, let's dive in. So a typical scenario we go through all the time is, let's say you're at home, you're getting ready to do your taxes, which are due next week in case you still haven't done them. And you used TurboTax, which takes all of your login credentials to all of your financial institutions, effectively the keys to your financial kingdom. Is this secure? It's easy to kind of abstract away and pretend that we have this secure, reserved, untappable, unspoofable, dedicated connection straight from your computer to TurboTax's data center. But this is not how it really looks, and it's not how it really works. In reality, your data is bounced and relayed between dozens of computers over cables, satellites, airwaves, on its way between your home and TurboTax. It's basically a giant game of telephone played out in a fraction of a second by computers. Every one of these computers along the way can see all the data that you're sending that gets passed through it. So if this is how it works, how can we ever get away with sending sensitive data over the internet? How do we achieve this when we know that the reality is completely different? So let's start with the first hurdle. How do we obtain privacy when everything we send can be seen by anyone along the path? Just think for a moment how impossible this and contradictory this task sounds. It's analogous to having a very nosy parent who listens to every one of your phone calls. They can hear everything. How could you ever hope to achieve privacy when someone is always listening? So let's see. The method our computers use is based on a mathematical technique called encryption. Encryption doesn't try to hide the data. It doesn't try to prevent anyone from seeing it. It works by a totally different principle. Instead, encryption works by erasing the meaning from the data before it leaves your computer, like so. So we see that the image and the caption transforms to a completely meaningless form that looks like random noise. In fact, it is indistinguishable from random noise. And it's only in this form that it conveys no information about the original message. It's therefore useless to anyone who might see it, and therefore we can safely send it over the internet. When it's received by the intended recipients, they'll be able to restore the meaning by subtracting out the random noise that was added, and they'll be able to recover the exact original message. So how's this done? All of the math in this presentation, and indeed most of the math in cryptography, is based on something that I'll call clock math. Now, clock math is easy to understand because we've grown up with it, we're all familiar with it. Unlike the number line, which stretches to infinity, on a clock, the numbers loop around forever. So instead of growing and having more and more numbers, we have a finite set of numbers that we're restricted to. Further, and this is somewhat unintuitive, clock math supports all the normal arithmetic operations. Aside from counting, we can add, subtract, multiply. We can even implement a form of division on clock math, and we'll see more of that later. So the only thing you'll need to understand encryption is adding and subtracting on a clock. So I can guarantee all of you will be able to understand this. So this is how encryption works in 3 simple steps. First, you start with the message that you want to encrypt. We'll call that message N. Second, you have to choose a number at random from the available numbers up on the clock. We'll call this random number R. Now, there are two important rules about this. So the first is kind of inherent in the name. It has to be chosen randomly. But moreover, every one of these numbers on the clock has to have an equal chance of being picked. And we'll see on some future slides what can go wrong if you don't meet that guarantee. So third, and this is the final step of doing encryption, you simply add R to N, but you do this addition on the clock. So the number, if you have two numbers on the clock, whenever you add them, you always end up at another number on the clock. You can't grow to any number higher. So let's kind of see this in action. Oh, and then we'll call the result, once it's been encrypted, we call that C, which stands for ciphertext. So let's say the message we want to encrypt is 7. We'll set the hand of the clock to 7. The next step is picking a random number. We can use, let's say, a 12-sided die. It's very convenient in this case because the numbers on that die will match the numbers on the clock. We give it a roll. We see what number we get. Let's say a 10 pops up. All we have to do is advance 10 steps on this clock, and we end up at 5. Now, 5 is the encryption of message N using the random value, which we call the key, of 10, and the ciphertext is 5. Now, it's very important that, actually, before I say that, the reason that this encryption works, the way it erases all information, you can think about it like this. Because the die roll is completely random, you have an equal probability of any one of these 12 values for your ciphertext. So from the point of view of anyone who intercepts the encrypted value, that encrypted value, from their point of view, it's just the result of your die roll. Now, it's your die roll plus the number you started at, but they don't know and they can't know what number you started at because, again, they're limited to seeing just 12 possibilities. And then to decrypt, if you know what R is, the person on the other side who receives the encrypted message 5, they just go back 10 steps. So they subtract by 10 and they'll end up back at 7, which is the message. Now, something that's critically important is you can't just, if you don't have a 12-sided die, you can't just take two 6-sided dice and roll them and add them together. And the reason is that wouldn't give you an equal likelihood of choosing any possibility. For example, you can't get a 1 from rolling 2 die. The minimum number you can get is a 2. Also, rolling a 7, if you're familiar with any dice games, is 6 times more likely than rolling a 12. That's just because there are more ways you can roll a 7 than, whereas rolling a 12, you have to get 2 6s. So if you do have these biases, the result is disastrous, and we can see that here. So this slide shows what happens when the randomness isn't uniform. On computers, all information is represented as bits, so either 1 through 0s. So when computers encrypt, instead of choosing a number from 1 to 12, all they have to do is basically a coin flip. They just have to choose 1 or 0. And then whether it's 1 or 0, they add that on the clock with just 2 possibilities, will result in either 1 or 0. And that's the results of the encryption. But if the computer had a coin that was biased, you'd end up seeing some of the original signal of whatever you're encrypting show through. So these images that look grainy or fuzzy, these are the results of encrypting it, but with a coin that is biased. So here we see a coin that will only have heads 10% of the time and tails 90% of the time. We can still make out most of the image. Conversely, if we were biased towards heads rather than tails, then we get kind of the inverse image, but we can still make out patterns. It's only when the coin is perfectly fair with a 50-50 chance of either 0 or 1 that you can erase all the meaning, and basically the entire image becomes nothing but noise and no signal. So that's what we see in these middle images. There's no distinguishable patterns that we can make out. So encryption solved the problem of communicating private data over a public channel. But it's now given us another problem, which, so if you and I meet in person, we can agree on what R to use for the message I'm going to send you later. But if I'm meeting you or connecting to your computer over the internet for the first time, and we never had a chance to meet in person to exchange or agree on a key, we're kind of stuck in this catch-22 situation. We can't get to the point of agreeing on a key, because if I were to roll some dice on my side, how do I tell you what my result is without that result itself being intercepted? So the problem that we're facing, it sounds like it's impossible to overcome. How can two entities who've never before interacted end up agreeing on an R value to use without anyone else on the internet along the way being able to see what that value is? Incredibly, it's not impossible, and there is a way to do this. It was invented by Whitfield Diffie and Martin Hellman in the 1970s. Their colleagues told them that what they wanted to do was impossible, but they persevered, they kept looking for a way, and they discovered a way. It's actually surprisingly simple. So to illustrate this, let's kind of see what it is that we're trying to do. We have two entities, Alice and Bob. They're meeting for the first time in public. Let's say they're in a very packed but quiet room where everyone can hear every word that's spoken. There's silence, and then Alice says a number. Bob says another number in response. And after these two speak their numbers, both Alice and Bob know exactly what number the other one is thinking, but no one else in the crowd can figure out what this number is. So isn't this incredible? You're probably wondering, how did they do this? It seems like a feat of magic. But the math behind it is probably something you learned in middle school. It's just the math of exponents. So to start, Alice and Bob both pick a number. Alice picks Y, or Alice picks X and Bob picks Y. Now, neither of them speak this number out loud, they just keep it in their heads. Now they both raise this number. They take some base and they raise it to the power of their number. And then they map that result to somewhere on a very big clock with P possible values. So P is a huge number. It's so big that all the computers in the world can never count up to it. But they fit their numbers A and B somewhere on this gigantic clock with a huge range. And then once they have those numbers, they can speak it out loud to each other. So the reason this is secure is mapping a very big number to somewhere on a smaller range is, this particular problem is called a one-way function, because it's easy to compute A given X, and it's easy for Bob to compute B given Y. But if you know B, there's no easy way to compute what Y was. Or if you see Alice as A, there's no easy way to compute what her X is. So it's fine for Bob and Alice to share these numbers. They aren't giving up the secret numbers that they're holding in their heads. Now, once they share these values, they have everything they need to figure out what the other person is thinking. And it works like this. Bob takes the number that Alice said, this A, and raises it to the power of his number. And Alice does the inverse. She takes Bob's number and raises it to the power of her number. And just given the properties of exponents, the result will be the same. And it's just because of this equation. But importantly, if you don't know X or Y, there's no way to figure out what R is. So because X and Y never left Alice's or Bob's heads, no one else in this crowded room can figure out what R is except for Alice and Bob. So now they have a way to, whether they're in a quiet room where everyone can hear them, or if they're sending data over the internet, Alice and Bob can, on the fly, generate a R value known only to them, even if you see everything that is exchanged between them. So this technique is incredibly useful. It enables not only agreeing on R values or keys between people who have never met, but that in itself is what enables encryption to be used over the internet in a practical way. So when your computer sends private information to TurboTax, both your laptop and TurboTax's server did the same exact protocol to agree on the same R value, which will then enable an encrypted message to be sent. So you encrypted this by adding your random value to the message, you send it over the wire, it's bounced around, eventually ends up at TurboTax's location. They know that same R value, they can subtract it out, and then they get your data. But as we've seen so far, you may have noticed it also has some limitations. So the first is we only get one R value out of this protocol at a time, which means we can only encrypt one message with this. Secondly, over the internet, how do we know that we're actually talking to TurboTax and not some hacker who's impersonating TurboTax? Instead of being TurboTax or our bank, it could be some imposter who set up a machine to look like your bank or TurboTax, and then they're just taking your data. So these are two problems that aren't solved by any tools we've looked at yet. But let's start with the first one. How do we take a single random number and generate multiple random numbers from it? So here's a little comic, which if you're familiar with programming, it might make sense, but the basic idea is a number that's random, chosen once, can't be reused and still maintain the property of being random. It just becomes a constant at that point. So how do we reproduce randomness? Is there a way to turn one random number into unlimited random numbers? On its face, this kind of sounds crazy. You can't copy random numbers because then they're no longer random. But if we could figure out a way to reproduce randomness, it would be extremely useful, because it would mean we could encrypt unlimited amounts of data with a single secret that we got from a single run of the Diffie-Hellman key agreement. So after that one interaction, we could encrypt as much data as we wanted, megabytes, gigabytes, hours worth of Netflix movies, you name it. So can we generate random numbers deterministically? This almost sounds like an oxymoron, combining the words random with deterministic. However, this is actually the foundation of almost all cryptography. Every encryption algorithm is itself an algorithm that takes a single small key of, say, 16 characters, and from that small random value can use it to produce an endless sequence of random bits. And with those endless bits, you can encrypt messages of any size or even multiple messages. Hard drives full of data, so you could have multiple terabytes worth of data on a single hard drive, can all be encrypted just starting with a single random value that's only this long. So this is 16 characters. That's the size of a key, which is commonly used in encryption. And there's effectively no limit to how much data you could encrypt with just one random value that's the size of these 16 characters. So how do we turn one random number into many? Here, just as an example, we'll look at an algorithm invented for this purpose. It's invented in 1986. It has kind of a funny name called Blum, Blum, Shub, after its three inventors. But it's a nice example for illustration because it's so simple. It can be described in just a single line seen here. So what this says is, all we do is we take a number that we start with, which the number that we start with we call the seed, and all we do is square it over and over again. And every time we square it, we're doing it on a clock with m elements. So in this example, I have m set as 253. And let's say the seed number, so the one random number that we're starting with, let's say is 7. Maybe we did a Diffie-Hellman protocol. We got 7 as our results. So that's the number that we're going to start with. Now let's see how we can generate unlimited numbers of bits using this approach. So to start, we'll start the clock hand at 7, which is our seed where we're starting. And then the algorithm says we need to square this number and then see where we end up on the clock. And then if the result is odd, we'll output a 1. If it's even, we'll output a 0. And we just keep doing this as many times as we want. So we square 7, we get 49. 49 is odd, so we output 1. Now we square 49. So now here's where we run into clock math. Normally, if you square 49, 49 times 49 is 2,401. but we have only 253 possible numbers here. So what's really happening is we're looping around this clock many, many times, and then we're finally stopping, in this case, at 124. That's where you would end up if you try to represent the number 2,401 on this clock. You would, in the same way you might ask, what time will it be 100 hours from now? You're going to get a number somewhere between midnight and 11 p.m. You aren't going to end up with a number in the hundreds. In the same way, we end up at 124, which is even, so we output a 0. And we take 124, square that. That's again going to be a larger number than 253, but we stop at 196, which is even, we output a 0. And we just keep doing this, jumping around the clock in a very unpredictable way until we have as many bits as we want. So even though this process is deterministic, it was proven by Blum, and Shub that it's computationally infeasible, or you can think of it as an intractable problem to distinguish between the bits that we generate from this process and a purely random sequence of coin flips. So if you don't know the seed, it's impossible to figure out, is this sequence generated by Blum, Shub, or is this generated by a bunch of coin flips? So if we use this approach together with Diffie-Hellman key agreement and encryption, this alone is enough to be able to basically start a private communication channel with another party and send as much data as you want to them. However, we still don't know if the person on the other side is who we think they are or who they say they are. For that, we need another tool. So the problem that we're facing is it possible to speak in a way that is both distinct and universally recognizable, yet in a way that no one can copy, duplicate, imitate, or impersonate? And indeed, math does make this possible, and all of internet security depends on this. So a famous person once said that the internet is a series of tubes. A lot of people laughed at him for that characterization, but I think that's a useful analogy for the problem that we face. Imagine if the internet is just a series of tubes that everyone is speaking into, and they're hearing the sound come out. The internet is like that in a way because we have this tube that we can put bits into and we get bits out. But how do we know where these bits came from or who sent them? We know all bits are copyable, so how can you make bits that can't be copied in a way that sound like they came from someone else? And that problem is the magic of digital signatures. Before we get into how digital signatures work, we need to briefly cover how do you do division on a clock, which in itself is a very interesting problem. So what does it mean to divide? We're used to like 8 divided by 4, we get 2. Or if you have some odd number like 7 divided by 2, then you end up with fractions like 3.5. But notice on the clock, we only have whole numbers. There's no concept of fractions. So that makes division has to be defined somewhat differently. And it turns out that we can implement division by realizing a clever trick with inverses, which is that division is really the same thing as multiplying by a number's inverse. So instead of saying, I want to divide by 5, you have to say, I want to multiply by 1/5. Whether you divide by 5 or multiply by 1/5, you get the same results. So that was the first realization. So for example, x divided by 3 is the same as multiplying by 1/3. But notice that we don't have any fractions on this clock. So how do we multiply by inverses? What is an inverse? And if you think a little bit more about what an inverse is, you might come to another realization that an inverse is any number that when you multiply by that number, or if you multiply any number by its inverse, you get 1. And that actually is something that we find on clock math. It does exist. So in the normal sense, 3 times 1/3 equals 1 because they're inverses of each other. But on this clock of 11 elements, there's another way to think of an inverse, which is that 3 times 4, so 3 times 4 is 12. But on a clock with only 11 elements, we end up stopping at 1. So 3 times 4 on this particular clock of 11 elements is 1. Therefore, we can say 4, in a sense, is the inverse of 3. when we're dealing with a clock of 11 elements. So let's test this behavior. Let's say we start with 3, or we'll start the clock at 1, and we'll just keep multiplying by 3 and see what numbers we get. So 1 times 3, we get 3. 3 times 3, we get 9. 3 times 9, we get 27, but on this clock, we'll loop around twice to get to 22. And then we'll go 5 more steps to end up at what normally would be 27. So if we keep multiplying by 3, we see the sequence 1, 3, 9, 5. Now let's see what happens if we start multiplying by the inverse of 3, which is 4. So 4 times 5 is 20, but on a clock with 11 elements, we get to 9. So it's like, we'll loop over 11 times and we'll have 9 left over to get to 20, so we get to 9. What happens if we multiply 9 by 3, or sorry, 9 by 4, we get 36, which on a clock of 11 elements, we'll loop around 3 times to get to 33, and then it will go 3 more steps, and we'll get to 3. And then we've already seen 3 times 4 gets us to 1. So if you look at this, when we kept multiplying by 3, we got the sequence 1, 3, 9, 5. Now, when we're multiplying by 4, which is the inverse of 3, now we're walking backwards, 9, 3, 1. So 4 is behaving just like 1/3 on this clock map. And it turns out that every number, when the number of elements on a clock is a prime, then all these numbers actually have inverses. So just to give you another example, 6 and 2 are inverses of each other, because 6 times 2, again, is 12, which comes out to be 1 on this clock. You can also say 7 and 8 are inverses, because 7 times 8, you get 56, which if you divide by 11, or if you loop around 56 times, you'll end up stopping at 1. So we can multiply, divide, add, subtract. We can do all these normal operations. And this will be key to how we can create voices that can't be imitated on the internet. So it takes advantage of this property where sometimes it can be difficult to find what an inverse is. Now, in the case we looked at, it was easy to come up with inverses because the number is very small. We could check every possible other number to see if it's inverse very easily. But when the number is very big and when the number of elements is the product of 2 primes, if you don't know what those 2 primes are, then it's not easy. It's actually very difficult to compute an inverse. So we can use this fact to build a system that allows us to speak in voices that can't be imitated, but can be recognized by anyone. The way that works is we'll publish one number, P, which will be public and known to everyone. But the inverse of that number, let's call that S, will remain secret, and we'll keep it only to ourselves. So that allows us to solve this problem that Queen Alice faces. So Queen Alice is a queen of her kingdom. However, she's very reclusive and doesn't like to be seen by her people. Yet to serve as queen, she still has to issue royal decrees. How are people to know that a decree really came from her and not some usurper? Maybe she died years ago and someone's taken her place and they don't know about it. And note that this is exactly the problem we face when we try to access websites online. We don't go to see these websites in person. We're just getting bits through the tubes. How do we know that they're actually coming from the locations that are claimed? So again, we can use ClockMap to solve this problem. The queen behind our castle walls has 2 numbers. Her secret number S, which she treats as like her digital signet ring, and N, which is the product of 2 primes that are known only to her. She has a sign put out in front of the castle which lists the queen's public number P and N. So everyone in her kingdom knows P and N, but only she knows S and N. When she needs to make a royal decree, she speaks it out through a megaphone. She gives her decree as this number M, and then she gives another number along with it, which you can think of as like her signature. It's just the decree raised to the power of her private number and then mapped to a clock of N elements. Now everyone in her kingdom, even if they hear these numbers secondhand, say from someone at the tavern, they can validate that it came from the queen. So even if through some elaborate telephone game, people, even if they didn't hear it directly from the queen's megaphone, they know it came from her. And the way they check that is simply, they take her signature, raise it to the power of her public number P. And if and only if the message equals this result, is the signature valid and everyone knows it's from the queen. If it's not, then everyone knows it's fake. And this works just, again, due to some properties of exponents. So the way to think about this visually is, if you know the inverse, the queen knows how to, from a given starting message, kind of rewind it back through the division. And then everyone who knows how to multiply can play it forward and get back to the message. And only if you use the correct inverse does that whole operation work out. So have you ever wondered how your browser knows that it's actually at chase.com and not some hacker's website? Chase.com is actually using, in all secure websites where you see the lock icon or the HTTPS, are using the same exact math as Queen Alice. And your browser, like her subjects, is able to authenticate the website's message. So your browser knows Chase's public number, Chase's web server holds the private number, and therefore your browser is able to validate that the bits it receives must have come from Chase and no one else could have produced them. So now we're going to kind of change things up a little bit. We've seen how to secure data as it travels in flight over the network of the internet and makes its way through the wires. But how can we use math to protect data over the long haul when it sits idle on a disk or thumb drive? And this is actually the problem that Ilya and I and a few others on this presentation, Mark, Wesley, helped design and create over our years at CleverSafe and IBM. So we'll see, is it possible to, we'll see how using some clever math, you can make it such that you can protect something that you don't actually have access to. Even though it's in your possession, you can neither look at it nor can you destroy it. If you could build a system like that, it would be the ultimate data storage system, because effectively you'd be impervious to being hacked, scrutinized, or having your data exposed. And simultaneously, you'd be immune from having your data lost or destroyed due to some act of negligence, some accident, or disaster. So let's see how, just using some kind of magical math, we can store data in a much better way. So Alice comes to Bob with an urgent request. He says, "They're after me. I need to go into hiding. Can you hold these documents?" Bob says, "I'll protect them with my life." With that, Alice hands the documents over, and then she's off. Several weeks later, Alice comes back to Bob. "Hey, do you still have my documents?" He reports that, "No, I held out for hours, but the waterboarding finally did me in. I'm sorry, I don't have them anymore." He says, "I'm sorry, you didn't have to do that." Said, "I would do anything to keep you safe." And Alice replies, "No, I meant literally, you didn't have to do that. The math kept my data safe." So how can this be? How can math protect Alice's data? Even though Bob's given it up to the authorities and he lost it, how can Alice not be bothered by the fact that Bob has completely failed in his duties to protect her data? So let's, again, kind of see the math of how this works and how it can be done. So it's based on something called secret sharing. So Alice has her true secret, we'll call it S. This is the data that she needs to keep secure from anyone seeing it. And further, it's very important that she not lose it. So encryption doesn't solve this problem, because if you encrypt data, encrypting data will protect it from being exposed. But if you have a data loss event and you lose either the key or the ciphertext, you won't be able to recover the data. So this is something that Alice needs to keep both confidential and available. You can think of it as like a Swiss bank account number. You wouldn't want that number to be exposed, because then anyone could spend your money. But again, you also don't want to lose it, because if you forget that Swiss bank account number, now you've also lost that money. So think of S as kind of that Swiss bank account number that she needs to store very securely. The first thing she does is she places S on a graph at point y equals 0. And X is the value of her secret S. Then she constructs a random equation that passes through this point. Now it's very easy to just come up with a random equation. You set S as kind of the constant term, and then you just have random coefficients, and now this is your random equation. So it's very straightforward to generate a random equation that will go through a certain point at y equals 0. Now this graph goes on, it extends to infinity, it goes on forever. And this allows Alice to generate basically an infinite number of points, as many as she wants. And now Alice can give each one of these points to one of her confidants. So Bob, Tom, Jim, Ian, Lee, Max, they each get their own briefcase containing one of these point values. But the important point is that individually, each of these are useless. None of them can be used on their own to determine S, nor do any of them actually have any information at all about S. Moreover, some of her confidants might lose them, but she would still be able to recover it in the future. So now that her secret has kind of been safely distributed among these 6 people, she can delete her copy as she goes off running and hiding. And let's say in the meantime, Ian gets hit by a bus. He never wrote down where he stored his documents, so that's kind of lost to the world with him. Now Bob, we know he was picked up by the authorities and tortured, and he had to give up his number. The authorities now have that. But so long as at least as many points survive as there are terms in this equation, she can solve for the original equation, and then therefore she can recover her secret. So these 4 surviving points are enough for her to get her data back. But the authorities who only have Bob's piece, or maybe they have Bob's and maybe Jim was hacked, he didn't even realize it, so they have Bob's and Jim's pieces. That's not enough for the authorities to reconstruct the equation. The authorities would have to compromise at least 4 of these individuals in order to have any hope of learning Alice's secret. So this is the basis of CleverSafes and now IBM's data storage technology. It lets you store data in a way where individual parties, they might be servers or hard drives, it doesn't matter if they get hacked, and it doesn't matter if their hard drives fail or if the site that they're at burns down. So long as enough of them survive, you'll be able to get your data back. So now we're going to move into some very unbelievable math, which is how do you make, is it possible to convince someone that you know something, let's say a solution to one of the greatest unsolved mysteries in mathematics, without revealing that information to anyone? Moreover, could you do this with a very small amount of information, even though the solution might be hundreds of pages long? And it turns out that this is possible, and it will enable and has enabled applications of enormous practical value. In the future, they could even transform the economy as we know it. So let's consider the following example. Alice has been working in her basement for years on one of the greatest unsolved problems in mathematics, known as the Riemann hypothesis. It's considered so important that the Clay Mathematics Institute actually has an open prize of $1 million to anyone who can solve it. So let's say Alice finally discovers a proof, and she's so excited, she can hardly contain herself. She calls her colleague Bob to tell him the good news. So she says, I've discovered a proof of the Riemann hypothesis. It's over 500 pages long. Bob, of course, knows everyone's working on this problem. No one's been able to solve it. Alice has a reputation as a prankster, says, I don't believe you. Now, of course, Alice might prove to Bob that she has the proof by sending it to him. But if Bob is unscrupulous, he might try to claim the prize money himself. Or if it gets intercepted along the way, someone else could steal it and try to claim the prize. So instead, Alice generates what's called a knowledge argument, which is a short message, only a couple hundred characters long. Moreover, it reveals no information about her proof. However, it does prove to Bob that she has it. So she generates this proof, this knowledge argument, I should say. She says, take a look at the short number. And then Bob, after looking at that and checking it, is entirely 100% convinced. He's blown away, and he's convinced beyond any doubt that Alice does indeed have a proof of the Riemann hypothesis. And this technique can be used to prove any claim that can be checked by a computer. So even though you aren't showing that claim to the other person, if a computer can check it, then you can use this technique to generate a knowledge argument, which then anyone else can check. So how is it that Alice can give Bob something that can fit on the back of a napkin, and yet prove to him beyond all doubt that she possesses knowledge that would fill a book if it were written down? So it's all, one of the easiest ways to explain this is in terms of a famous problem in computer science called the graph recoloring problem, which is, given a graph, is there a way to color these nodes using just 3 colors such that no 2 adjacent nodes, let's say 7 and 8, have the same color? So here's a solution to that particular graph. So note that no adjacent nodes here share the same color. Now, if this is our example, how could Alice prove that she has a solution to this problem without disclosing any details of her solution to Bob? Now, this seems completely implausible, but actually in 1989, 3 MIT computer scientists showed a way of doing it. And the first step in seeing how it can be done is to realize that there actually, once you discover one solution to that coloring problem, you immediately, for free, get 5 other more or less identical solutions just with the colors swapped around. And that's because there are 6 permutations of doing the coloring. So each of those kind of gives you another way of representing that same solution. So you use that property. So you may have originally colored it like this, but you could also color it like that or like this. And by iterating over all 6 equivalent colorings, every pair of nodes will see all 6 of the possible color permutations between them. So based on that, Alice can now perform the following protocol, where she can prove to Bob she knows a solution without revealing anything about her solution to Bob. So it would work like this. First, she chooses one way of coloring it. Next, she covers all the nodes with hats. And then she invites Bob in and she says, Bob, my solution is under these hats. I can't show you the whole solution, but if you pick any line, I'll show you the 2 hats that are connected by that line. And you can verify that the colors are different. So Bob picks this line, Alice reveals the 2 hats, and Bob verifies, yes, the colors are different. Now, Alice has a very good chance of fooling Bob because maybe she has a nearly complete solution, except Bob didn't choose this particular edge, which would have revealed that she doesn't actually have a complete solution. So this only slightly increases Bob's confidence, but because Bob gained no information, Alice can repeat this protocol again and again as many times as needed to convince Bob. So she kicks Bob out of the room, she erases her solution, and then she recolors it, covers it with hats again, invites Bob back in. He picks a different edge, and then Bob sees again the colors are different, so I'm a little bit more confident. And after, let's say, 100 iterations of this, Bob can be extremely confident that Alice does indeed have a solution, but he's gained no information about her actual solution, because every time Alice recolors these nodes, so even if Bob keeps picking the same line each time, every time he does, he's just going to see what seem to be random colors. So he's not learning anything about the true colors of these nodes. Now, this can also, it wouldn't be very convenient if, let's say, Alice wants to write an article in the newspaper to prove that she has the Riemann hypothesis. If it requires interaction, then every reader of the newspaper will have to go through the same protocol with Alice. It's not going to be very efficient. She's going to spend the rest of her life doing this for the millions of people that want her to prove it. But there is a way to transform this into a non-interactive proof. And the way you do that is basically you replace Bob with a public function, which everyone can follow. So the function will be making the choices instead of Bob. And so basically what Alice would do is she'll encrypt her solution, and then she'll put that encrypted solution through a function that she doesn't control. That function will tell her what edge to reveal, and then she'll publish the encryption keys so that anyone can decrypt it and see, yes, those are different. And she can do this many times, and then she can publish her list of encrypted solutions and all the revealed answers, and then anyone can read that and become highly convinced that it's correct. However, none of them will gain any information about her actual solution. Now, what's really incredible is that, well, you're probably thinking, what good is graph coloring solutions? That doesn't seem very interesting. But this graph coloring problem is very special in computer science in that it's related to an equivalent problem called 3-SATs. The 3-SAT problem asks whether a given logical circuit has an input which will give a certain output. Therefore, there's an equivalence between if you know a certain solution to a 3-coloring problem in knowing a solution to any given logical function. So if you have a function that, let's say, checks, is this a valid proof of the Riemann hypothesis, then you can convert that statement to a solution on the graph coloring problem. And if you can then prove to Bob, I have a solution to this graph coloring problem, then he can know, yes, you indeed do have a solution to the Riemann hypothesis. So you can prove anything. We gave that example. You can, now here's where you can get to something that's practically useful. You can even use this to prove statements about encrypted transactions. So this is useful for cryptocurrencies. Right now, every cryptocurrency transaction is in the public for everyone to see and scrutinize. But there are some new cryptocurrencies that are using this exact technique in order to have completely anonymous transactions. So these are transactions that people can validate even though they can't see them. So that's very interesting. They don't know how much money is sent or from whom or to whom. They know it's a valid transaction, but they don't get any details about it. It's useful in clouds. It's also useful for authentication. So you could, for example, prove that you know a password, but you don't have to give your password over to someone in order to prove that you know it. So now this is the most implausible thing that we'll cover today. It's also the last topic. We have about 10 minutes left. So I'm just going to walk you through an example of what this is and how impossible it seems. So Alice puts all of her financial data, let's say her tax documents, into a locked container and sends it to Bob. She asks, hey, can you do my taxes? They're in this locked box. Don't open it. Bob says, sure, no problem. Bob waves a wand and taps his heels together 3 times. And when he's done, her completed tax forms have manifested within this locked box, even though he never opened it. He sends the box back to Alice, who opens it and finds her completed 1040 forms ready to go off to the IRS. Now think about how absurd this is, that Alice can put documents in a sealed container, send them to a tax preparer to have them done. Bob, her tax preparer, is able to do this without ever opening that locked box, without ever learning anything about her financials. He was never given the key to unlock this box. Yet after he waves his magic wand, her completed 2019 tax forms appear ready inside this locked box. So this seems like absolute madness. Surely this isn't possible and I'm hallucinating. You're just becoming part of my hallucination right now. But actually in 2009, Craig Gentry of IBM showed that this is indeed possible. So let's see how. So 1978, it was noticed that there was an encryption scheme called RSA that had this funny property. It was just kind of a curiosity. It wasn't very useful. But it turns out that you can take 2 numbers in RSA and encrypt them. So we have 2 and 3. Let's say we encrypt both of them. Now, even if you don't know the key to decrypt this, if you multiply these 2 ciphertexts, these 2 encrypted values together, you'll get a 3rd encrypted value, which when you decrypt, will have the results inside it. So this this kind of representation of that. So encryption of A times the encryption of B will give you the encryption of A times B. Therefore, when you decrypt it later, you'll get the answer A times B. And then later in 1999, another encryption scheme called PIA was found to allow people to add two encrypted values together without decrypting them. So again, you can have two numbers, 3 and 5. They're encrypted. However, you can take the two ciphertexts and add them together. And then when you decrypt it, you'll get the answer. So the sum of those two numbers, 3 and 5, is 8. So again, this was just a curiosity. People thought it was a little bit interesting and odd. But it turns out that these were kind of the building blocks of a much greater realization, which is that it doesn't seem all that useful if all you can do is add or multiply. But it turns out if you can find an encryption scheme that lets you both add, so RSA only let you multiply numbers, but you couldn't add them. PIA encryption let you add them, but you couldn't multiply. If you could find an encryption scheme that let you both add and multiply, it turns out that you can do a lot more than just implement a pocket calculator. You can actually do far, far more. You can actually do anything that a computer can compute on encrypted data. So let's see why this is. So in 1937, Claude Shannon proved that with just and, or, and not, those logical operations, you can implement any computable function. And what's interesting is that only if you can do both addition and multiplication can you implement these logic gates. So if you can add them, let's say you can subtract. So subtraction is just a special case of addition. If you can do 1 minus a, this is equivalent to the logical not operation. If you can multiply two numbers, this is equivalent to the logical and operation. And if you can add and multiply, you can implement the or function. So once you have both addition and multiplication, you can implement any logic gate. And with any sequence of logic gates, you can implement any circuit which performs any computation that a computer is capable of doing. So this is what allows Alice to encrypt her financial data. She sends it to Bob. Bob works on that encrypted data by doing these operations on it while it's still encrypted. He ends up with a still encrypted result. He sends that encrypted result back to Alice, and only Alice, who has the keys, can decrypt it and get her completed tax document. So there are a ton of applications and potential for this. Actually, every one of the infinite pieces of software that are possible could be rewritten to work on encrypted data. There are already some applications of this where you can, instead of sending your DNA off to undergo some genetic test, you can use this technique to encrypt, let's say, the base pairs of your DNA. You send your encrypted base pairs to the lab. The lab then runs the test without ever seeing your DNA. You get back an encrypted bit, which, let's say, when you decrypt, it'll be 1 if you have the markers for this disease, or 0 you don't have the markers for this disease. Only you learn that result. The lab never learns it. The lab never saw your DNA. Only you learn whether you have this disease or not. So there are actually already prototypes of systems that use that technology. One of the last projects I worked at IBM and presented at last November was based on another homomorphic encryption scheme where you could have a system that could give you encryption keys. However, it couldn't see what those encryption keys were. And literally, your imagination is the only limit for other applications. There is one downside, however, that I should mention, is that it's slower and less efficient to run a computation on encrypted data. That's because each bit in the scheme is typically expanded by about a factor of 10,000. So while a genome is about 750 megabytes and can fit on a CD, on a single CD, if you expand that by 10,000, now you're up to 7.5 terabytes, which would fill a large hard drive. So it's still, there's a cost in terms of being less efficient. However, there are many applications where it's worth paying that cost if you can preserve your privacy. So what have we learned today? We've seen how math secures the internet, how we can hide data that everyone can see. We can agree on secrets in public. We can speak in ways that can't be impersonated. We've looked at new math that will change the world. So how you can protect data without actually having it, how you can check proofs you can't see, and how you can work on data that you can't access. So with that, I'd like to open it for audience discussion. So if you have anything to ask, unmute yourself and be happy to take any questions.